So this is Tom Roby from U Connecticut, and he will be talking about dynamical algebraic combinatorics and homomesy an action-packed introduction.
Thank you all for staying so late, especially those of you in time zones that are 6 hours, or if there's anybody here from Japan, you get the special prize for still being around at this early hour of the morning. Oh, great. Yeah, good. Okay. Here's the abstract, which you should have already read if you cared. Here's the acknowledgements, which I'll blow over quickly. The slides are now posted on the AlCoVE site. So if you want to go follow along there and look at details or, figure out a new way to escape, go ahead. Please put questions in the chat. I'm not monitoring the chat, but I'm sure a moderator will, or maybe one of the nice people I'm acknowledging on this slide will answer things for me. So dynamical algebraic combinatorics covers a range of different possible things. And in a 25-minute talk, I'm just going to focus on a few examples and a few themes. So here are the themes. The themes are questions of periodicity and order. Let's see, I hear background noise, but that's probably just people leaving. So that's fine. Okay, so anyway, there's questions of, how many times do you, if you have an action that's generated by a single element, so it's a cyclic action, you can ask questions for how many times do you run it before you get back where you started. You can ask questions about orbit structure, questions about homomesy, which is a relatively new term that I'll define carefully in a few slides. And then often, not always, but in many cases, the key to understanding some of these things is to find a nice equivariant bijection that helps you understand a more complicated action in a simpler way. And then I'll take one of the actions that we're looking at and lift it from the combinatorial setting to the piecewise linear and birational setting so that you have iterated functions of labelings of posets, say, with real numbers or even variables. But as David Hilbert said, you should always begin with the simplest examples, and in a short talk like this, we'll probably end with them as well. So here's cyclic rotation of binary strings. So this is a very simple map. If you just, I see, right, I can't click on that, I forgot. But you take the numbers, you take all these bits, you shift them one slot to the right, and then you bring the 0 at the end around to the front. So that's a rightward cyclic shift. And it's easy to see that if you do that 6 times, you get back where you started. So the periodicity is clear here. And the orbit structure is also very nice. You'll see that every orbit size has to divide 6, or n in general. And to talk about the notion of homomesy, I need to give you a statistic first. And of course, we don't need an equivariant bijection when this map is so simple. But so here's the, I'd like to define an inversion of a binary string as a pair of positions that are out of order. So if you look at the string 0, 0, 0, 1, 1, all the zeros come before all the ones. If you look at, say, this string here, can you guys see when I highlight? Then there's the first one is out of order with 3 things. The second one is out of order with 2 things. So there are 5 total inversions. This is generalized from a well-known permutation statistic, but it works equally well for multi-set permutations or bit strings. And if you look at the average number of inversions, you find that that's always equal to 4 for each of these orbits, even if the orbits aren't the same length. And so this is an example of the homomesy phenomenon. Your ingredients are that you have a set S, an invertible map tau, such that every tau orbit is finite. So I think of the action is generated by the cyclic group generated by tau. And then you've got some statistic that gives you some measurement, and you look at the average of that measurement across all the orbits. So if that's constant, if you have constant average over all the orbits, then you say that this triple exhibits homomesy. And in this case, you say that the function f is homomesic with average c, or sometimes we'll just call that c-mesic. So there are lots of examples of these things, and I'll try to give you some. If we look at inversions, the number of inversions as we just saw, then the average of that statistic on bit strings under cyclic rotation is k times n minus k over 2. And the proof you can look at more quickly in the slides. I'm just going to blaze through it. But if you consider superorbits so that you can make all the orbits the same length, and then you track carefully what happens when you make an adjacent swap, that 1, 0 becomes a 0, 1, then as you go through this orbit, you're always losing one inversion until you go around the bend, which happens during the last talk of a long conference over Zoom, and then you get +5 escape points. So there are other homomesic statistics as well. For example, if you just looked at the indicator function of any given position, that actually would also be homomesic, and I'm sure you can see why with a minute's thought. So now let me give you another action on bit strings that's a little bit more complicated. We're calling this Coxeter toggling independent sets of a path graph. So probably we're all familiar with what an independent set of a graph is. In this case, I'm only interested in the path graph, like as shown in the example, and that for me corresponds to a binary string with no adjacent one. So this is the indicator string, the vector that tells you whether I'm in the independent set or not. And since I'm in the independent set in slots 1, 3, and 5, I go 1, 0, 1, 0, 1, and then 0, 0. So these are well known to be counted by Fibonacci numbers. And Jessica Stryker, generalizing an earlier concept of Cameron and van der Vlas, talks about that there's this notion of toggling. So here's the technical definition, but the idea is, let's look at an example. So if I toggle at a slot, I can either, since the first slot is in the independent set, I can take it out and I'll still have an independent set. That's a special feature of independent set toggling. And so this becomes a 0. Now I toggle in the second slot, and what happens? I can add, this one is not in the independent set, so I can add it back in and I'm still good. But now when I try to toggle in slot 3, if I added that 1 in, if I added that element of the set in, then I would not have an independent set. So I can't do it, so I leave it alone. It's like the doctor's maxim to first do no harm. Now in slot 4, I do have a 1, so that can always become a 0. And then in the last slot, that 0 can become a 1. And so doing that toggling action from left to right once at each thing is what I'm going to call my map phi up here. And it's easy to see that these toggles are involutions, and also that they commute if and only if they're non-adjacent. Okay, so when Mike Joseph and I first looked at this, this action on the advice of Jim Prupp, we found that the order of the map grew much faster than just cyclically rotating bit strings. In fact, you can see these are sort of wacky numbers. They're not even increasing there. They kind of go up and down depending. And so for example, for n equals 6, instead of getting back where you started in 6 steps, it takes you to 231 steps. The actual number of orbits was a well-known number in OEIS, as you can tell by the small value, but we didn't understand why at first. But what it means is that for those of you who know the cyclic sieving phenomenon, that this you're unlikely to find cyclic sieving in this kind of a situation, or natural cyclic sieving. You can probably always cook something up. But we can still find a natural homomesy, and so I'll show you that next. So here's an example. If I start with this particular bit string with no 2 consecutive ones representing an independent set, and I apply iterations of phi, which is this map where I'm just toggling from left to right, then I get this. This shows you the full orbit, and we call this the orbit board because we've kind of divided it up into rows and columns. And if you add along each column, then you notice that the output you get is palindromic. So that's saying that there's a kind of symmetry in how many times you get a 1 in the first slot with how many times you get a 1 in the 7th slot. And so we express that in the language of homomesy by saying that centrally symmetric indicator functions are zero-mesic on these phi orbits of independent sets of a path graph. It's also easy to see that if you take twice the value in the first column plus the value in the second column, that's 1-mesic, which means that 2 times 4 plus 2 should be 10, which is the length of this orbit. And that'll be, by the symmetry, that'll also be true there. So here's a, So the proof of this wasn't obvious to us at first, and it took a while to come up with. Here's a larger orbit board on which I'll demonstrate what you need to do. It turns out that you can partition the ones in this board, which of course determine the location of all the entries, into ones, into snakes of ones. And the way you do that is either you've got something below and to the immediate right, or you have to go 2 slots over to the right. And this gives you a bunch of things. There's the red snake. You can see that this sort of brownish one on the bottom wraps around. And I'm skipping this over for lack of time, but you can look again later if you want. But it turns out that you get these snake compositions. It's unnatural to define a composition depending on whether you had to jump 2 columns or just 1 column to get to the next element of your snake. And it turns out that these snakes are just cyclically rotating, these compositions into 2s and 1s. And so this was the entry in the OEIS, compositions into 2s and 1s modulo cyclic rotation. So we noticed the homomesy, but besides that, this helped us understand other things about the action, like why most orbits had size congruent to 3 times n minus 1 mod 4, and why the number was this low element in OEIS. And you might think this is a very specialized action, but it turns out that this actually doesn't depend on the order in which you do the toggles. Even though those toggles don't commute in general with each other, you can use some elementary Coxeter theory and show that no matter what order you toggle, as long as you toggle once at every vertex, you end up getting the same homomesy result. So that's an interesting thing to look at if you like that kind of stuff. Okay, and so this is really the last example that I'm going to do, except I'm going to lift it to several levels. So anti-chain row motion on posets. So this is an old map that you can understand combinatorially most easily as you start with an anti-chain, and then you can make the downward saturation of that, which is just you look at all elements that are less than or equal to any element of the anti-chain, and you end up with this set in the example. And then you can complement to get what you might call an upset or an order filter. And then if you look at the minimal elements of that, you get an anti-chain. So all of these maps are bijections. They're all invertible. And when you chain them together, you get the definition of anti-chain row motion is kind of a 3-step waltz. So a lot of people have looked at this map, but the term row motion that Stryker and Williams came up with has stuck. And one of the first examples of homomesy, although it wasn't without using that language, is a conjecture of Panyushev, which was proven by Armstrong, Stump, and Thomas, that says if you do this row motion on certain classes of posets that come up in representation theory, I'll show you pictures in a minute, then over every orbit you have the same average. The statistic here is the cardinality of the anti-chain. So in our language, the cardinality statistic is homomesic with respect to the action of row motion on anti-chains in root posets. What's a root poset? Well, I'll mostly be focusing on type A3, but I swiped the tech code for this picture from the Stryker-Williams paper. And here's an example. When you've got the A3 root poset, then you've got an orbit of size 8, an orbit of size 4, and an orbit of size 2. And if you check the average cardinality for each orbit, you find that it's 3/2, which is what it should be, n/2. If you tried to do this, well, yeah, that's another story. And just because it'll come up later, right, so now what other posets does this work for? So it works for the root posets. Jim Propp and I, in our first foray into homomesy, decided to check whether it would work on a row motion on anti-chains of a rectangular poset. So here we've got the poset a 2-chain cross a 3-chain, and you can see, at least in these 2 examples, which cover most of the anti-chains, not all of them, that you're getting the same average cardinality. Here's the complete 2x2 case. And so now I want to return to the themes, right? One of the themes was periodicity, And the periodicity of this was shown that it's a very small periodicity, just A plus B, was shown back in '74 by Brouwer and Shriver. Van der Vlos figured out what the orbits looked like in 1993. And then he joined forces with Peter Cameron and figured out a different way to understand this map that I'll talk about in a few slides. So Jim and I proved that this statistic was that we had anti-chain cardinality being homomesic in these rectangular posets, which are a kind of minuscule poset, and this whole story has been generated to other kinds of minuscule posets, if you know what those are. And then the key thing here, that the key tool that we use to make this work is an equivariant bijection. And so this equivariant bijection is something called the Stanley-Thomas word. It came up, it's described quite briefly in a paper that Stanley wrote. And it gives you a non-obvious bijection between anti-chains in a rectangular poset, and again, binary strings, which here we're representing with +1 and -1. And it's equivariant in the sense that as you cyclically rotate the string, that corresponds to anti-chain row motion. I don't want to give you the impression that you can always find a nice equivariant bijection that shows you these things, but when you can, it's really useful because basically you figure out most of what you want. And so we use this kind of a bijection to derive refined homomesy results for fibers and for antipodal points in A cross B. And I'll just describe those briefly because they'll come up in the birational setting as well. So it turns out instead of computing the entire anti-chain cardinality, if you restrict your attention to just one of those red fibers, you can think of them as rows and columns. We call them fibers for historical reasons of avoiding other confusion. And along this fiber, if you just count how many anti-chains you have, then that actually is also homomesic. And those two homomesies for each fiber add to the 6/5 homomesy we saw earlier. And similarly, if we go on the fibers in the other direction, so whichever one of rows and columns you didn't talk about before, then the average is 2/5, and those again sum to 6/5 because there are 3 of those. And so there's the technical statement of those, which you can look at later if you're interested. And so I guess to tell you the full story, how much time do I have left? I have no idea when we started.
So you have like 8 minutes or so.
8 minutes, okay, yeah. Or so, I like the or so, thank you. So this row motion operator on anti-chains makes equally good sense on the corresponding order ideals. And you can think of this 3-beat waltz as starting 1 beat later, and then you can start with this order ideal, complement, look at the minimal elements, which will be an anti-chain, and then saturate the anti-chain down. So you also, if you like, the other way to think about it is a operator on the upsets. And I think that's what I'm doing here. So this is the row motion. So you can actually do this row motion map via toggling. So this is what Hugh Thomas and Nathan Williams call row motion and slow motion. And so here, this is the original notion of toggling. If you toggle at an element of E of your poset, what that means is you add E into, here I guess we're talking about upsets. If it's not in there, and as long as you add it, you're still in the space of upsets. You can take it away if it's in there, and taking it away would leave you in the space of upsets, and otherwise you do no harm and you leave it alone. So Cameron and Van der Vlos showed that applying these toggles from top to bottom along a linear extension of a poset gives row motion on upsets of P. So a lot of people have seen this story, and I think I'm going to blaze through it quickly. I'll show you the equivalent thing for anti-chains, since that's less familiar. But here you would toggle that. You can't toggle that out. You can't toggle that out. You can toggle that out. You can toggle that out. You can't toggle that in. You can't toggle that in. And that gives you the same thing as if you did the 3-step process. So let's take a look at that for anti-chains. Now, one difference between anti-chain toggling and order ideal toggling is that you are unable to, you can always toggle an element out of an anti-chain because removing an element from an anti-chain always leaves you an anti-chain. So it makes the definition of toggling somewhat simpler, but then the relations between them get a little more complicated. And so Mike Joseph showed in 2017 that if you apply these anti-chain toggles from bottom to top along a linear extension of P, that gives you row motion of anti-chains in slow motion. So I'll do this example a little bit more slowly. We have to start at the bottom. So we look there. If we added it in, it would not be an anti-chain, so we leave it out. Now here, so we toggle there, we can always toggle the element of the anti-chain out. Then here, we can't toggle that in because it would not be an anti-chain. These two elements wouldn't be an anti-chain. But can we toggle this one in? I know this is a bad time to ask for audience participation over Zoom, so I'll just tell you yes. And then you can toggle that one out, and you can't toggle that one in. So this is a 6-step, an A times B number of step process in general for computing this. And so here's this gives the same result as if I'd done the 3-step waltz process. Okay, but so why is this useful? One reason it's useful is that it gives you a natural way to generalize things to polytopes. I know that some people in the audience like polytopes, and here you even have you could talk about a tale of 2 polytopes from this work of Stanley going back to '86, where he introduces 2 polytopes associated with posets, the chain polytope and the order polytope. All they are labelings of some poset by real numbers, but subject to some inequalities. So in the case of the chain polytope, your inequality says that you can never, the sum along any chain can never be more than 1. So this is an example of something that's in the chain polytope, but it's not order preserving. It's that 0.7 is smaller than the 0.2. So it wouldn't be in the order polytope. So here's something that would be in the order polytope where it's an order preserving labeling like that. And so then the upsets or order ideals or order filters correspond to the vertices of the order polytope, and the anti-chains correspond to elements of the chain polytope, correspond to the vertices of the chain polytope. So Einstein and Propp defined and analyzed piecewise linear toggles and then lifted them to the birational setting. And so here's how you do this for the chain polytope. So the way you want to toggle at an element is you say, okay, compute all the possible sums along maximal chains that go through the element you're trying to do it. And then take the max of that and then subtract that from 1, and that's a way of guaranteeing that you're still in the chain polytope. So it should make some sense. So in particular, in this case, we can look at this chain through, which has a sum of 5. This chain has a sum of 5. This one has a sum of 6, but that's the largest one with a sum of 7. So that's the max. And so then I change the value here from 0.1 to 0.3, which is 1 minus 0.7. Okay, so that's how you do a piecewise linear toggling. And now I'm about to show you 60 slides in less than 60 seconds. So here we go. Actually, it's only 30 slides, I guess. Those of you who are very fast at computation can follow along. But at each of these steps, I'm just doing exactly what I showed you. And lo and behold, I get back where I started. Amazing. Why should this be periodic with the same periodicity that we had in the combinatorial setting? So, that's sort of a miracle. And for a long time, there was no proof of this that didn't lift to the birational setting. And I think Hugh Thomas and his collaborators have something now, but it still uses some highfalutin algebra to do the heavy lifting, is in my understanding of it. So once you've got the piecewise linear toggles, and so then you've got this piecewise linear row motion, you can lift it by detropicalization. So when you tropicalize, you replace plus with max and multiplication with plus. When you go the other way, you go from you take max becomes plus and plus becomes multiplication, and so minus becomes divide. And so this formula here ends up converting when you geometricize or detropicalize to this formula where we put a C in because it helps us keep track of some things. The 1 you can't see when you have powers, but the C is a little bit better. So we've C, the minuses divide by all of this, max becomes sum, and all these sums become products. Yeah.
2 more minutes.
Great, thanks. So So now we can define birational anti-chain toggling. So lifting this combinatorial map, and BAR-metion, you won't be surprised, is the birational map obtained by applying the birational anti-chain toggles from the bottom to the top. So here's an example of this, where, so I'll do this one a little bit more carefully. We have to, there are two paths here, and so we have to take C and divide by the sum of those two paths, the products along those two paths. Now, at the next place, X, there's only one path going through, so we do that. It'll be symmetric for Y, and then for Z, you'll get some cancellation. And so that four-step toggling operation is one iteration of BAR-metion. So now, if you do it again, you get this. Do it again, you get this. You do it the fourth time, you get back where you started. And if you don't think this is miraculous, then maybe you work in cluster algebras or something. But if you try this on generic posets, it almost never works. Mostly you get incredibly horrible rational expressions. And so let me just tell you some properties of BAR-metion. So the BAR-metion is the parallel lifting to the birational row motion that Einstein and Propp studied. But the order of BAR-metion turns out to be just A plus B, just like it was for the combinatorial and piecewise linear settings. The homomesy results for anti-chain cardinality in the set lift to all the way up to the birational setting. And we can lift this Stanley-Thomas word. It no longer is an equivariant bijection, unfortunately, because if it were, we could actually prove the periodicity of this, which is a hard theorem. So our proof of the periodicity for BAR-metion relies on the proof for BOR-metion and translating things over via some nice isomorphisms. So we can't, so we don't have we don't get the easy proof that we did in the combinatorial setting where the Stanley-Thomas word was a bijection, but it's still an equivariant surjection that cyclically rotates with BAR-metion. And so it can be used to prove homomesy, but not periodicity. So here's a full orbit of BAR-metion for the generic labeling of a 2x2 poset. And you can see, and I've written the Stanley-Thomas word, and you can see it cycling around with these labelings. And so that's, I mean, there's no time for full-on definitions or anything, but I just wanted to give you the flavor of what these things look like in a variety of settings. So just to summarize, I think this is my last slide before the references, is that there are these four themes we're interested in: periodicity, orbit structure, homomesy, and equivariant bijections. I'd like to point out that for those of you who are interested in cyclic sieving, that instances of cyclic sieving are also ripe for homomesy hunting. And the situations in which you have maps built up by toggles, by involutions, can be particularly fruitful. And combinatorial objects can be discrete shadows of these other objects at the higher levels. So I think that's it. Slides for this talk are available on the AlCoVE website. Soon they'll be available if you type Google Tom Roby, but I can't quite get my, my website correctly configured to right place. Thanks so much for coming and staying for this talk. I'm glad there was a game ahead of time to entice you here. And there are references you can look at your leisure. Thank you very much.
Thanks, Tom, again. At the beginning. So I haven't interrupted you, but there has been a whole conversation about the orbits and the periodicity. So if you open the chat, you will be reading like a lot of messages about it.
Yeah, I was hoping that that my collaborators, what was hilarious?
I think that Karen's messages about your daughter working through.
Oh, Oh, I see. Yeah, right. Yeah, because I always talk about waltzing.
You waltzed in at the right place at the right time.
Yeah.
So there is one question that just arrived. Does anything work on another maximal parabolic quotients of Bruchar order?
So,
Wait, in what sense are we on such a quotient?
Alexander?
Yeah, so Sam is answering that it's certainly nice for minuscule heaps, but beyond minuscule, I don't think we found a lot of examples. It seems to be quite specialized, the posets for which you get periodicity. And the ones for which you get periodicity, you can find, I don't think there's all that much known beyond what's in the paper that Daria and I wrote about birational row motion, which we're now calling BOR motion for birational order row motion. I don't think there's all that much that's been done beyond that. Maybe Sam knows a few more examples. Yeah,
I
Sam.
think Sam probably knows the most examples because he recently wrote a summary, also not in the operational setting.
I love these rich discussions that take place behind my back when I'm giving a talk.
Yeah,
But I like them more when they're behind other people's back while I'm watching their talk.
Okay, so let's thank Tom again. Oh, another question. Has there been anything done concerning orbits under non-cyclic groups?
Yeah, so the notion, you're quite correct that the notion of homomesy makes perfectly good sense for any group action. And but the trick is that if a statistic is homomesic for a cyclic subgroup of a group, then it's automatically homomesic for the larger group because all you've done is taken smaller orbits and made them larger. So what you really need are examples of where the group is, where you have homomesy for a larger group, but it isn't true for any cyclic subgroup. And so I think there's an example in a paper of Anne Schilling and Nicolas Thierry and maybe some other people from AIM where they had one example of that. But that's another great thing to look, we'd like to have more of for sure.
Cool. What paper?
I don't know, maybe is Anne there? It's probably too late for her, she went to bed.
No,
And it's in California.
I can send it to Dari, no problem.
Thank you.